Yeah, hi guys, welcome to the present video. So in this video, we are going to see uh, the MHSET electronic science question paper. Okay, so few of the questions we are going to see in this session, guys. Okay, so before going into the main content of this video, so regularly I'm telling that this video is specially designed for the electronics candidates, okay, for BTech, BSc and MTech and MSc. Okay, so as an electronics background, whatever the competitive examinations you are preparing for, so in this channel, only the previous year question papers and along with that one, the topics related to electronics and communications will be discussed here. And whatever the topics I'm discussing apart from this topic, so if you want to get any some topics to be cleared, then you just mention the topic in the comment section. Okay, that I will try to discuss in the next video. Fine. And whatever the state eligibility test examination question paper I am going to tell, so this examination happened in 26th September 2021. So as a part one, we are going to discuss here a few questions, and in the next parts, okay, based upon the number of views, okay, and as per the support, okay, I will do the few more parts to complete the complete questions regarding this 2021. Fine. So please don't forget to share this YouTube channel link in your respective groups, guys. Okay. And now, so it is a question paper that I got from the official website of the Pune University. Okay, so from this one I got, and here we will discuss about few of the questions, guys. So while coming to the first question, a silicon PNP bipolar transistor has the following parameters. So collector current is given, and common emitter current gain factor, that is HFE or the beta, is given as 120, and operational temperature T is equal to 300 degree kelvins, and determine the mutual conductance of the small signal transistor. Okay, so basically the conductance of the transistor can be taken as, just a minute guys, yeah, the conductance of the transistor can be taken as Gm is equal to IC divided by eta Vt, and eta depends upon the silicon and germanium, so that becomes is equal to one or the two, and where Vt can be taken as a volt equivalent temperature, or else the temperature equivalent voltage. Generally we will call as a temperature equivalent voltage, or else simply we can call this one as a thermal voltage. Okay, and this thermal voltage Vt is equal to kT by Q. K is the Boltzmann constant and Q is the charge of the electron. So substituting both these two constants, you will get as the complete expression is T divided by 11,600. Okay, so for example, if they mention that the room temperature means, then in the place of T we have to substitute the 300 degree kelvins and then calculate. So at room temperature approximately we will get the thermal voltage as a 26 millivolts. Fine. And now the transconductance Gm is equal to IC divided by, in the question they mentioned it is a silicon transistor, so let's take the eta as a 1 and Vt is equal to, here Vt I am taking as a 26 millivolts at room temperature. And if you check the question here, the IC is mentioned as a 6 milliamperes. So let's take the 6 milliamperes here, 6 milliamperes divided by 6 milli. Now cancelling of both these two, so 6 divided by 26. So all of you simplify this one. So what is the value we are getting? 6 divided by 26, 0.23 mho. Okay, or else the Siemens. So we are getting the 0.23 as an answer, and you can take the option A is a correct answer. Got it? Option A is the correct answer for this question. Okay, next go to the second one. When an electron is thermally excited to conduction band in semiconductor, an electron is surrounded by what? Just check about the options once. Very less number of occupied energy states, less number of unoccupied energy states, large number of unoccupied, large number of occupied energy states. So first of all, if an electron is excited to the conduction band, okay, that means we are giving some additional energy. Got it? So as per the energy band diagram concept, what we can take is that, just a minute. So energy band diagram concept means we will take like this, right? and it is the conduction band and it is the valency band, right? And if you supply any some additional energy, external energy is nothing but it might be the thermal energy or else it might be the some electric potential. Okay, so whatever the energy we are giving additionally, so these electrons this additional energy will make the electrons to excite from valency band to conduction band. If they are exciting from valency band to conduction band, then what will happens here, one hole will takes place and here the electron will come. That means we will call this one as a generation of electron hole pair. Whenever any one electron is excited from valence band to conduction band, it is called as a generation of electron hole pair. If the electron de-excited to the valence band, we will call this one as a recombination. Okay, so generally if from any one semiconductor, if you are expecting the huge amount of conduction, means the generation rate has to be greater than comparing with the recombination rate. Okay, fine. Anyhow, so by taking some external energy, the electrons are exciting to the conduction band. And in the question, they mentioned that occupied states and the unoccupied states. See guys, here, what is the meaning of this occupied and unoccupied means, whenever any one hole is formed in the valency band due to the excitation of the electron, then this one is called as a unoccupied state. Because hole is nothing but vacancy of an electron, and we will call this one as an unoccupied state. And here, whatever the electron is jumped, and this conduction band can be taken as a occupied state. Okay, so like this we can define that unoccupied and the occupied state. That means electrons are jumping to the conduction band which is surrounded by the occupied states. Got it? So based upon this concept, like occupied and unoccupied means unoccupied states can be taken as a holes, occupied states can be taken as a electrons here. Fine. So based upon this concept, now we can opt this answer. So please have a look. When an electron is thermally, means we are giving some external thermal energy. Due to this one, the electrons are excited. Okay, so now let's have a look. Very less number of occupied states will be there in the conduction band. Very less number of unoccupied energy states, large number of unoccupied states, or else a large number of occupied states. So what might be the answer here? We can take option D as a correct answer. So in the conduction band, the electron is entering into the electron is surrounded by the large number of occupied states. Okay, and whatever the hole is there in the valency band, the hole is surrounded by the large number of unoccupied states. That means option C is worked out for the holes present in the valency band, and option D work out for the electrons surrounded in the conduction band. Okay, so it is a concept regarding the occupied and the unoccupied states. Fine. Now let's move to the third question. So here they mentioned that N channel MOSFET is preferred than P channel MOSFET. Because what? Few points are given here. Input impedance of N channel is higher than the input impedance of the P channel. And next, input impedance of P channel is higher than the input impedance of the N channel. Electron mobility in silicon is smaller than the mobility of holes, and electron mobility in the silicon is larger than the mobility of the holes. Okay, it is what they mentioned here. Just a minute, guys. Yeah, these are the options, and from these options, what might be the correct answer? So why the conduction in N-type MOSFET, N-channel MOSFET is preferred than the P-channel MOSFET? So why? Because all of you know that mobility of the holes is less than the mobility of the electrons. Am I correct or not? Okay, so in the CMOS logic family also, in the CMOS logic family, generally we are constructing the circuit with the help of N MOSFETs and the P MOSFETs. But the speed mismatching will happen. So to match the speed, why the speed mismatching is happening? Because mobility of electrons is more. That means the N-type enhancement MOSFET will switches very quickly comparing with the P-type MOSFET. Why? Because the mobility of holes is less. So to match up the speed, we are doubling the size of the P-type MOSFET in the case of the CMOS logic family. So here, based upon the mobility issues, here we can take that why the N-channel MOSFET is preferred, because the electron mobility in silicon, not only in silicon, in any type of semiconductor, Okay, electron mobility is larger comparing with the mobility of the holes. Okay, and if you want, you will get the readings also. Okay, readings means you will get the values also regarding this mobility of electrons and holes. Okay, just wait a minute. Yeah, mobility of electrons and holes in the silicon as well as the germanium. So these values also I will give. So please make a note of this one. So electron mobility 1400. Okay, usually we can take the volts as centimeter, I mean units as centimeter square per volt second. So 1400 and 3900. It is in the case of germanium and it is in the case of silicon. That means electron mobility is greater in germanium comparing with the silicon. And while coming to the hole mobility in silicon is only 450, and while coming to the germanium it is 1900. Units are centimeter square per volt second. Centimeter square per volt second. Okay. So mobility wise, germanium is top. Sorry, yeah, and germanium is top in both the holes as well as the electrons mobility of the charge carriers wise comparing with the silicon. Okay, fine. So based upon this one, while coming to this one, so here option D can be taken as a correct answer. Next we will go to the next question. Yeah, fourth one. So for a p-type material, the Fermi level lies at which point? Usually if you take the p-type semiconductor, the Fermi level lies at where? Is it in the conduction band, nearer the valence band? Okay, where exactly it locates? So here also the same concept we can discuss, that initially if the semiconductor is not at all doped, then the Fermi level will lies almost at the middle of the forbidden energy band gap, correct? And if I take the n-type semiconductor, then the Fermi energy level lies nearer to the conduction band. We can take it as the EFN. If I take the p-type semiconductor, okay, then the Fermi level lies nearer to the valency band. So we can take like this. Got it? So now here the expression is also there. So I will give that expression also. The Fermi energy level of the p-type semiconductor, that is EFP, it can be given as EV plus KT ln of NV by NA. Okay, so it is the expression. So from this expression we can tell that whenever the temperature is increasing, see here the temperature is, if we are increasing the temperature, then what's happening to the Fermi level of the p-type semiconductor? Fermi level of the p-type semiconductor gradually moves up and it reaches to the intrinsic Fermi level. Okay, that means to the extrinsic semiconductor, whether it is a p-type or the n-type, if you are keep on increasing the temperature, then the extrinsic semiconductor converts into intrinsic semiconductor at one particular temperature. It is the most important point that you should know, and we can justify this point based upon this expression itself. Okay, in the same way you can take the expression for the EFN also. So I mean for the n-type semiconductor, the expression can be given as EC minus KT ln of NC divided by ND. So from this one what we can tell, that whenever the temperature is increasing, then EFN, what happens to the EFN? EFN is decreasing. That means EFN gradually moves down and it reaches the intrinsic Fermi level. So whenever the temperatures are increasing, these extrinsic semiconductors are converting into intrinsic semiconductors. Okay, fine guys. So these are the 4 questions in this session, and the remaining questions we will discuss in the next video. So if you got any new points, then please make a note of those new points, and we will discuss all these rest of the questions in the upcoming session. Okay, so I'm requesting that all of you please subscribe the channel and then tap the bell icon, and please share this video link to your in your groups. Okay, please circulate and try to maximize the views, okay, as well as the subscribers. Okay, why? Because then only it will be motivates to me to do the further videos in this channel. Okay, So thank you very much, guys. Bye bye. All the best.